Learning target 1.11. I can define and write a balanced equation for alpha decay. So alpha decay occurs when an unstable radioactive nuclei, for instance, americium-241, decays and emits what we call an alpha particle. So an alpha particle is just a helium nucleus. So helium with a atomic number of 2 and a mass of 4. That's what it's emitting, and you can kind of even see it right in here. There's 2 protons and 2 neutrons in that alpha particle. So it emits that alpha particle along with some energy, and we say that it is undergoing alpha decay. So the second thing we need to figure out is how do we write a balanced equation for alpha decay. So the way I start, especially with a problem like this, is I start with what my parent isotope is. So my parent is always the guy that you're starting with, which is in this case americium-241. So that's the mass of americium. Now I got to figure out the atomic number. The best place to do that is the periodic table, and I can see down at the bottom the atomic number for americium is 95. Then that parent isotope decays into a daughter isotope, which in the picture is represented by neptunium-237. And then I look up at the periodic table and I see that neptunium's atomic number is 93. But that's not the only thing that is decayed. There is also an alpha particle emitted, so I add that to the end, and that is just a helium nucleus that has atomic number of 2 and a mass of 4. So this is the complete balanced equation for the americium decay, alpha decay. Couple things I want you to notice. The mass that I started with, right here, 241, is equal to the mass that I end with, 237 plus 4. So this still obeys the conservation of mass. Also, note my protons. I started with 95 and I finish with 95. Okay? These are the clues that will help you write balanced equations for alpha decay. Our individual example for learning target 1.12 says, in the space below, write the equation for the alpha decay of actinium-230. Place a box around the daughter isotope. So pause the video, try this, and then resume when you want to check your answer. So in order to do alpha decay, we start with our parent. They give us the parent. The parent is given to us right here, actinium-230. So if I don't remember the atomic number for actinium, or perhaps even the atomic symbol for actinium, I can always look up at my periodic table. I see it, AC, with a periodic or with a atomic number of 89, and I know the mass, I know the isotope, it's 230. That's my parent. It decays into a daughter isotope and my alpha particle. So I'm going to leave a space for where I'm going to write my daughter isotope, because I know, since it's undergoing alpha decay, that it's going to emit an alpha particle. Doing it this way makes it a little bit easier for me to figure out at least what the atomic number is of my daughter isotope. And I know that my daughter isotope has to have a total, my daughter isotope plus my alpha particle have to have 89 protons, because actinium has 89 protons. So if helium takes 2 of my protons, I know that I have to have 87 left over. And if I look up at my periodic table, the atom or the element that has 87 protons is francium. Okay, and then I can also do the same trick with my mass, and I have 230 to start with. Helium took 4 of it, so I'm going to be left over with 226. So francium, 226 would be my daughter isotope. And the question asks me to put a box around my daughter isotope. So that is the final answer. Hopefully you got the same.